It's now also a great privilege to introduce the next speaker, Professor Cara Schwarz. She's an experimental thermodynamicist with nearly 20 years of experience in phase behavior measurements, and she's going to explain all of that, what that really means to us in a few minutes' time. She's well published with 70 publications in international peer-reviewed journals, 112 conference contributions. She has already graduated 5 PhDs and 12 master students, and another 7 PhDs and 7 master students who are currently enrolled. She has quite a substantial record of publication, and she's also a regular reviewer of a number of international journals. She's a member of the editorial advisory board of the Journal of Chemical and Engineering Data, and in 2020 she will chair the Phase Behavior and Fluid Property Symposium of the International Conference on Chemical Thermodynamics in London. Cora, we're looking forward to listening to you.
Thank you very much, Professor van Niekerk, for the introduction. Ladies and gentlemen, the Vice Rector, Professor Professor Kluter, Professor van Niekerk, friends, family, colleagues, everybody who has made an effort to be here today. I'm going to be speaking on the phase equilibria of fluid phase systems. And the reason I chose to talk about this topic is, in a way, this is the closest I could summarize what I have done in the last 20 years. So what does equilibria actually mean? So equilibria is the plural of the word equilibrium, and it basically says it is a state in which opposing forces or influences are balanced. It's a state of being physically balanced. It's a calm state of mind. It is, from a chemistry point of view, it is a state where its process and its reverse are occurring at equal rates, that you don't have an overall changes happening. So that is the one word, but I apply that to phase equilibria systems. And what are phases? Well, Professor Uptegan has spent quite a lot of time talking about the solid phase and the interference or the boundary between solid and liquid phases. I'm going to be speaking about fluid phases, which I'm going to define as a phase in which the molecules can move freely around. So you don't have a crystal structure that's actually impeding this movement. What you have are molecules that can move freely around. To most of you, that will mean a liquid and a vapor phase. I've spent a lot of my time working in the supercritical phase, but I'm not going to spend much time today on that. All you need to know is that's a high pressure gas which behaves very similar to a liquid. So what is phase equilibrium? Well, if I go back one slide, it's the equilibrium on the boundary. And it's a balance of temperature, pressure, and compositions. And how do I explain that to you? Well, let's look at the production of sparkling wine. And as an engineer, let's assume that my wine only consists of water and ethanol. So I'm going to ignore all the other little small components, and I'm going to put that into a bottle, and then I'm going to evacuate my vapor phase, and I'm going to put some CO2 on top of it. And I'm going to leave it in the fridge for a very long time. So what will happen with time is your carbon dioxide will diffuse into your liquid phase, and hopefully very little, but some of the ethanol and water will diffuse or evaporate into your vapor phase. And you're going to end up having an equilibrium between these two phases. So what is this equilibrium? Well, what are the compositions of both of these phases? How long does it take to reach equilibrium? And in fact, how do I actually know I am there? So today I'm going to be speaking about this equilibrium from a point of a couple of questions. And I'm going to look at, first of all, the thermodynamics of the phase equilibrium. Then I'm going to have a look at how you go and measure it, how you actually get there, or the processes that are happening getting there, how you detect that you are there, and lastly, how you quantify it. More from more of an overall view perspective of that. Ultimately, I want to have a look at the two questions. How long does it take for that carbon dioxide to get into that ethanol, and the ethanol and the water to evaporate, and how do we know that this process is essentially complete? So let's start off by having a look at the first topic, namely the background thermodynamics, because I'm going to repeatedly come back to that. So let's go back to my bottle. And the first thing that's going to happen is when you've closed that system, you've put everything in there, you're going to get some kind of mechanical equilibrium. And that means your pressure on your liquid phase and in your vapor phase is going to be constant. Followed from that, or the second requirement is thermal equilibrium. And that thermal equilibrium will basically mean that both your temperatures are constant and they are no longer changing. It's the easy part. The more difficult part to conceptualize is the chemical equilibrium. And chemical equilibrium will not necessarily mean that your compositions are the same, but rather that something called the chemical potential is in fact constant. So what is chemical potential? So chemical potential is the potential energy that each of these components have. So your chemical potential of your carbon dioxide in your liquid phase will be equal to that in your vapor phase. And the same will be true for your ethanol and your water. And this chemical potential will manifest itself through the compositions. So you're going to end up having 3 more relationships for this particular system. And importantly, those compositions are not necessarily constant. They are constant, but they are not necessarily equal to one another. So if we want to go and determine what these compositions are, as engineers, we're going to do some kind of calculations. And we have carbon dioxide, ethanol, and water in our system. And this is actually a very difficult system to model. So those of you who in the know will know we have dipole moments, we have quadrupole moments, we have hydrogen bonding occurring, and a little bit of a non-polar segment in here. And then because we have pressure, we cannot assume the ideal vapor phase. And if we put that all together, modern physics is not quite there yet. So even your state-of-the-art models cannot predict this particular system with sufficient accuracy over a very broad range. So what does that mean? Well, I'm in business. So I need to go to the lab and I need to go and do experiments. So therefore, ladies and gentlemen, there is a need for experimental measurements. So if I go back to my thermodynamics slide, how do I do these measurements? And after a whole load of mathematics, one comes down to Durham's theorem. And Durham's theorem says if I know how much carbon dioxide, ethanol, and water is in the system, and I go and fix 2 other parameters, Bob's your uncle, and you can go, once you've got equilibrium, and everything is in fact there. So what that means is if I know what my temperature is, I know what that volume is, or that volume is fixed, all these components, their equilibrium will, or you have a unique solution to that particular equilibrium. So let's go and have a look how we do these measurements. So what we're going to do is we want to simulate what's happening in our bottle, and we go and we get some kind of piece of equipment. So I've spent a lot of the last 20 years having a look at how we do these particular measurements, and there are a number of techniques. I'm going to only concentrate on a single technique today, and that technique is an analytic technique where we actually have to take samples. And the reason for that is we have a 3-phase system, and this is the only way I can get the required information. So I've got some kind of vessel, closed vessel, a vapor phase, a liquid phase, and my temperature is known and my pressure is known. And I now need to go and take a sample from that vapor and from that liquid phase. I can do that either by keeping it closed and taking small samples from it in a static method, or I can go and I can remove some of the material from both the vapor and the liquid phase. I can remix it and reintroduce it. I can go through one of these two different techniques. Importantly, both these methods will give you the same answer, and they will also allow for mixing to occur between these two phases. So now I know how I'm going to measure this data, but how do I know I am at equilibrium? How do I know I am at that, or how can I get to that point where everything is balanced? So let's go back to my bottle. And here we can see we have our 3 equilibrium criteria, and they still remain because thermodynamics remains there. You can't take it away. So mechanical equilibrium is generally, you generally get there very quickly, but so it's thermal and chemical equilibrium I'm actually going to spend a little bit of time on. And I'm going to just quickly explain what the driving force is. So when you have added the CO2 to your bottle, you need, and you're going to put it into your fridge. When you initially put that bottle into your fridge, it is at, say, 20 degrees Celsius. Your fridge is at 5 degrees Celsius, and there's a temperature gradient. And that temperature gradient allows for energy to be removed from the bottle so that your contents actually becomes less. So that is what our temperature gradient is. And although more abstract, exactly the same concept happens in for our chemical compositions. Again, we have a chemical potential difference, and because there's that difference in the chemical potential or the energetic potential of components, they will actually strive towards our chemical equilibrium, and they will get there. So we have a driving force of temperature and a driving force of pressure. Of chemical potential. So within my bottle, let's have a look at what's happening. So if we assume that the glass is now our bottle has now cooled down, but our contents is not there yet, the first thing, or one of the factors that are going to happen is heat transfer. So we're going to transfer energy or remove energy from the system, so our system is going to decrease in energy as it becomes colder, and that's going to happen through the wall from both our vapor and from our liquid phase. But because the properties of our phases are different, the one is a liquid, the other one is a gas, this may not necessarily occur at the same rate, so we're going to also have heat transfer between our 2 different phases. Analogous to that, we will have what we call mass transfer. So that is the movement of molecules of carbon dioxide and water molecules between our 2 phases in with exactly the same driving force that we have for our energy transfer, our heat transfer. So essentially, that is what's happening. But this is significantly more complicated than what one would actually think. And heat and mass transfer the mathematics becomes very complicated, and there's a lot of underlying factors that are happening. So if I go and have a look at a very extremely simplified manner where we have good mixing, the predominant forces that are there are convective heat and mass transfer. And a few slides ago, I spoke about the driving force. And heat transfer QH, the amount of heat we transfer, is proportional to this driving force, and so too is the rate of mass transfer. On the front of that, we have a proportionality constant, our heat transfer coefficients that we have on the front. And these transfer coefficients give you an idea or they are there to account for the movement of the molecules and how fast this process actually proceeds. But what makes this whole thing extremely complicated is the fact that these transfer coefficients are functions of both temperature, pressure, and composition. So during the process, they end up changing. Ultimately, putting this all together, we've got a very complex mathematical relationship with ill-defined and even at times undefined mathematical functionalities. So to go and solve this problem would probably take me longer than if I go and measure it. So at the end of the day, the answer with respect to phase equilibria is just leave it for long enough. Because if you leave put your bottle with your carbon dioxide and your wine in the fridge for long enough, it will get there, as long as you know how long enough is. So is that science or is it art based on experience? So if we don't know how long, or if we don't know if we're going to get there, if we can detect where we are there, it would also help us. And to answer that question, how we need to look at the question, or need to answer that, we need to pose the question, how do we know we are in actual fact at phase equilibrium? So let's go back to my bottle of sparkling wine. So if I want to know if I've got mechanical equilibrium, I can put a pressure transmitter in there. If I want to know if I'm at thermal equilibrium, I can go and put a thermocouple, or for those of you who don't know what that is, a thermometer in there. So I can measure that. But unfortunately, there's no magical device to measure chemical potential. Because what we normally do is we measure chemical potential by looking at the compositions. But measuring compositions is also not quite so easy. So what we very often do is we say, we've left it for long enough temperature, long enough for, and our temperature and our pressure is stable, we assume that our compositions are stable. But that's not necessarily always the case. So let's go back, let's look at one of my binary systems, my water ethanol binary system. So that is traditionally a very well studied system, but it has what we call an azeotrope. So I've just drawn briefly some of the phase behavior over here. And if we go and have a look at our high ethanol content, so if we have a very high ethanol content, say from about 70% upwards, what happens? Well, for a single degree Celsius temperature range, most of our data is in that range. In fact, for 80%, from 80% upwards, we're in about a 0.3 degrees Celsius temperature range. And ladies and gentlemen, that's about as accurate you can very often measure something. Might get down to about 0.1 accuracy, but if we go and depend on to know if our compositions are constant by having a look at our pressure and our temperature, we might actually not be there. So what does this end up making us do? Well, we allow our self-sufficient time to get to equilibrium, and when we do these measurements, we actually go and verify our equipment significantly. So we spend a lot of time proving that we can reproduce other people's data with our equipment to show that our measurements are in actual fact a reflection of reality. Again, is this art based on experience, or is this science? So lastly, I just want to speak about quantifying phase equilibria, and that is to actually do these measurements. And I'm not going to spend very much time here, because if you want to go and have a look more on some of these details, there are a couple of very good references in the piece I wrote. So as we previously said, pressure and temperature, rather easy to measure, but it's these compositions which are not that easy. So if we go and have a look, what we need to do, we need to make sure our sample is representative. In other words, the compositions, if we take a sample from these phases, it must actually represent what's inside each of our particular phases. And once we've taken those phases, we must be able to put it into our black box analyzer to get an answer out that is in actual fact true of what is in that phase. How we very often do that? Well, you take a big enough sample and that will happen. But the problem is, if you take a big enough sample, what's going to happen? You're going to disturb your equilibrium. Because if we go back one slide, we have what we call a closed system, so we've got known masses. So if we take too much material out, we're just going to go and disturb the equilibrium. The other thing you also need to do is, if possible, you need to go and take your samples simultaneously. So it doesn't help taking a sample from the vapor phase, leaving it for a few hours, and then taking a liquid phase, if you at all possibly can get around that, because what will happen then is you could get a disturbance of your equilibrium. So that makes sampling very difficult. But sampling is still the gold standard in the industry, and that's how we do most of our analytical phase behavior measurements. The alternative is spectroscopic and gravimetric measurements, but unfortunately a lot of these techniques are beyond what we can actually do at the moment, because you need big infrared or Raman spectroscopy measurements, or even a very large KMR, which unfortunately we cannot use for just these basic measurements. So ladies and gentlemen, coming to the end, I spoke about these 5 topics, and I posed 2 questions. How long does it take to reach phase equilibrium, and how do we know we are there? I don't have an answer for this, because this is very much system specific, but what I do know from my experience is that it's more of an art based on experience and intuition of the researcher doing it than an exact science. So as I come to the end of my talk now, I need to say thank you. And getting to this point has not been a solo effort. It's been something where I've had a lot of input coming into it. And the first set of people I need to say thank you to are all my students. I've had the privilege to work with you in your brilliant minds, and you have really brought a lot of input into me. I need to say thank you to my present colleagues and also my past colleagues, and thank you to those that are here, both here at Stellenbosch University and also the wider thermodynamic community. You've really given me a lot of constructive criticism. And then friends and family. You've kept me sane through this process. But I would be amiss if I didn't actually say thank you to a few people. And I'm actually going to do this part of this in Afrikaans now. So, Isak, 20 jaar terug het ek by jou met my studies as 'n nagraadse student begin, en jy het my begin op hierdie in hierdie gebied van fasegedrag, en jy het vir my die fondasie gegee. En hulle sê 'n huis is net so sterk soos sy fondasie. Baie dankie. Andrei, jy het in Isak se kantoor ingetrek 20 jaar terug, en jy het basies 'n groot rol in my lewe gespeel. Dankie vir jou insette en jou moeite, en dit is 'n voorreg, dit was en dit is nog steeds 'n voorreg om saam met jou te werk, en hopelik kan ons 'n hele klomp verder jaar saamwerk. Ansie. So ek ken jou al meer as die helfte van my lewe, en vandat ek 'n tweedejaars student was hierso, terug in die laat 90's, jy was my dosent, my skripsieleier, toe was jy aan die ander kant van die tafel as my examinator, jy was my PhD medestudieleier, jy het vir my, toe ek my postdoc by jou gedoen, en vandag staan ek langs jou as 'n kollega. Baie dankie vir alles wat jy vir my gedoen het, en dit was ook 'n voorreg om saam met jou te staan. But professional performance only comes with the support of those people around me. And here I've put some photographs. So, in his heyday, my daddy, thank you very much, Dad, for giving me a safe home to grow up in, for believing me and giving me every opportunity. Clary, she's my sister, she's sitting here in the front, she's my best friend, you're my rock. But just like Professor Guven Aptegan, I need to dedicate this talk to somebody. Ladies and gentlemen, I dedicate it to my mom. She's not with us anymore, but she brought me to where I am. Thank you.
So I now call on Professor Klute to give us a response to both of these oral lectures.
Thank you. Thanks very much, Professor Van Niekerk. Good evening, colleagues, ladies and gentlemen. Congratulations to our 2 new full professors, and I am sure that you enjoyed as much as I did listening to them. I want to briefly say something about what they said and how I understood this. Professor Ogdogan showed us the importance of basic research and the impact that that basic research actually has in the applications, and what one can do with knowing the real science behind an application. He indicated the importance specifically of physical and chemical characteristics in order to determine the yield of platinum, and specifically oxygen and temperature. He focused on the iron endpoint and the importance for high or low oxygen or iron in the mat, and how that in fact increases the yield of the platinum, and also then, of course, the other materials when you come to the product purification and separation. What I really liked is the way that you visualized your chemical reactions by making use of flame optical emission spectroscopy, and how that has also found its way into industry and saving the industry an additional, or giving them an additional profit, of course, of 15 million rand per year. So well done with that research. It's very impressive. I can say the same for Professor Schwarz. She really explained a very difficult concept in a very understandable way, in fact. Using a model, no model is ever simple. There are already 3 variables, there are 4 variables in terms of the carbon dioxide, the ethanol, the water, the temperature, the pressures, the forces that drive this thermodynamic equilibrium, the mechanical equilibrium, the thermal equilibriums, chemical equilibriums, and so forth. And I think that listening to you, I realized that it's not this easy, and this is why you need a little bit of that intuition. And you end off by really explaining that carefully, by saying that, you know, perhaps the question is really, how long does it take to reach phase equilibrium? And then, how do you know that you have reached equilibrium? And I was sitting there and I thought to myself, there are other phase equilibriums that also happen in our lives, and we're going to have some of that just now when we have some snacks. And I was thinking that some people, well, they know how long it takes to get drunk. But for many of them, they do not know that they are drunk. And then, and that's just another phase sort of equilibrium that we reach. So I really urge you not to take all the time to get to that point. And sometimes, and you also mentioned sometimes it's just intuition. Some people don't know that they are drunk. So with those few words, colleagues, we've really seen really top-class presentations here this evening, worthy of the 2 full professors here. We are fortunate to have you at this university, and thank you very much for the contribution that you are making to this particular faculty, to your departments, and the university as a whole. Let's give them another round of applause.
And I'm now going to call on Professor Hansi Kutze to thank some of the people involved and some other people, and also just, if you don't know, he was the previous dean before me, so I really respect him for that. And now he is the chair of the Department of Process Engineering, which has got, of course, a whole new phase equilibrium and dynamic tool.
Yes, Professor Klute, Professor van Niekerk, colleagues, ladies and gentlemen. On behalf of the faculty and the department, I want to thank you all for your presence here tonight. It's a very important night for both Guven and Cara, and I've sort of walked the way with them over the last many years. Guven maybe about 10, 11 years. Cara, as she mentioned, slightly longer. And they really appreciate everybody who's turned up. Without you, this night would not have had the splendor and the spark, because it's not nice lecturing to 2 or 3 people. The more people, the merrier. So when I start doing a word of thanks, it's always possible to leave out people, and if I leave out people, my apologies for it. Firstly, thank you, Professor Klute, for your attendance and your very good summary. Professor van Niekerk, and then to all the people who actually organized this event, especially Marley, who's standing there at the back. I think a lot of effort went into this, and yes, I think you probably did 90% of the organizing. And then she had some help from Portia Adams, who was responsible for the printing, and Marjorie van Rooij, who did the invitations. So thank you, and we look forward to the refreshments afterwards. And when a night like this, I think all the speakers always appreciate it if their loved ones and family are here. So thank you for those who supported both Guven and Cara. And yes, it's I think Cara's now sitting next to her dad. So Ernst Schwarz, thanks for attending. Thank you for all the support you've given Cara over the years. She really appreciates it. And I'm sure you are very proud of her. And also to her sister, thanks for attending. But also to lots of people and loved ones supported you. I think, yes, nobody of us can actually achieve something without the people close to us supporting us. And then Cara's already thanked him, but Isaac, thank you for attending all the way from the US. He didn't come specially for the lecture. He's actually here on a holiday. Last week was actually the department's 50th anniversary. We had a celebration. Isaac was one of the keynote speakers. And this week he's, I think, visiting some of the family. So he could have been with his family tonight, and he's here with us. So thank you very much for that. And then, yes, Dr. Reynolds and Isabel Geldenhuis and colleagues from Mintech, thank you for the collaboration with Guven. Thank you for coming all the way from Johannesburg to attend the lecture. As a department, we always appreciate the collaboration with industry, the funding from industry. Without it, no research would have been possible, because the university budget, or the funding we get from the Department of Higher Education and the funding from the Department of Science and Technology, can't actually fund these experiments. The experiments Guven was talking about are quite expensive. Probably not even thousands of rand per experiment, but 10,000s of rand. A special word of thanks to Professor Andre Berger and Stephen Bradshaw. I think you two had a big influence on the development of both Guven and Cara. Without your support, I don't think they would have been able to develop and achieve the rank of professor. So thank you for the infrastructure and the atmosphere in the department that can actually build young careers to the extent that we can actually promote people to professor, and we don't need to get people from outside to appoint them as professors. But as Cara and Guven has mentioned, you can't actually achieve anything if it's not for students and colleagues. And I think we are fortunate in the department that we get the very best of students, and we have very good lecturers and colleagues that can help us develop as academics. So for all of you, thank you. Thank you for your contributions. In engineering, academics can't really do research. To a large extent, we are research managers and we are soundboards. We can guide students to do certain things, but unfortunately, we don't have the time to do all the measurements. Although Cara still sometimes do some measurements in the lab, and I think Guven also still sometimes get to do that. And then I think lastly, I need to thank Guven and Cara. Without them, we wouldn't have had tonight. Tonight is about them. to celebrate their achievements, to celebrate their promotion. And they've earned it. They've earned it the hard way. They've earned it by many hours, more than the 40 that you get paid for. So I think we really appreciate it. Thank you for your lectures, that even an old retired professor like myself could understand it. Thank you for your inputs towards the development of the department and the faculty. And then I think thank you for the persons you are. In the end, it doesn't help that we achieve a lot, but there's, as we would say in Afrikaans, daar's 'n klomp lyke langs die pad. There's a klomp bodies that we leave behind because we only want to get to the top. So thank you for the fact that in all of this, you are still, we can still smile at one another. We can still appreciate one another. So thank you for that. And at the end of tonight, I want to wish you all, especially our two colleagues, the best for the future. May in a few years' time, you actually move on to become distinguished professors, and may your research careers and your teaching just go from strength to strength. Thank you, ladies and gentlemen, for attending.
Ladies and gentlemen, all that's left for me to say is that if you haven't seen it, the publications were distributed. If you don't have one, there's more here in the front, and I'm sure there will be more at the back. No, there's no more at the back, but you can collect them around here. And then we would like to invite you for a glass of wine, some snacks, and some non-alcoholic beverage as well. You go out the door at the left, just keep on going to the left, and it's right behind the elevators. And we look forward to meeting you there again. Thank you very much.